Okay. Alrighty. Let's finish up our, well, I have two more, but let's talk about qualitative and quantitative analysis a little bit more. And what we're going to think of in this one are acid-base titrations. And this is where we're going to use an acid or base reaction to determine an acid and base neutralization reaction. There we go. Use my words to determine the concentration of an unknown acid or an unknown base. Okay. This is technically called volumetric analysis. And if we remember when we're talking about a neutralization reaction, we're always taking some acid and some base, and they react together and to get water, as long as you have a hydroxide base, which most of the time we do, okay, and give us a salt, okay. When we do this one in the lab, we'll be using phenolphthalein as an indicator, and that turns pink. That's what this pink is here for. You guys will get used to this as we get our hands on some stuff as we do it. Okay. Let's look at some of this here then. Okay, PowerPoint wording me again. All right. So we start off with a sample of unknown acid or base concentration. And for this example, we're working with an unknown acid, but the process will be the same if you're working with an unknown base. Um, Lost my pointer. Okay. Um, we're going to react this with an acid or base of a known concentration. Since we know we're working with an unknown acid, we're going to use a base that has a known concentration to react with this. Okay. We're going to completely neutralize the reaction. That means we're going to get to the end point. The end point is this special point in the reaction. Okay. So when we're talking about end point, okay, we're going to say that the end point, the reaction is complete, right? There's only products in the mix. We could say a stoichiometric amount has been added. Okay. I should have left myself a little bit more room. Metric amount added. Yeah. And at the end point is the point where the balanced chemical reaction applies. Okay. So at any other point, there's going to be a combination of all four things in there: acid, base, salt, and water. Okay. At the end point, it's going to be only the salt and water. There's no acid or base left over. If you go beyond the end point, you're going to have more base in there than you need to, and it's not going to work out for us. Um, a good word for us to know at this point is titrant, if I could spell it. Titrant. Titrant is the thing that gets added. It's in the burette. So here, when you're putting the solution in the burette, that's what's going to work. So in our case here, the unknown acid is in the flask. The base is the titrant, and it is in the burette. Okay. We're going to add base precise amounts. That's why we're using the burette, so we can get a really precise amount of base added in there. And once we have the endpoint, there's a lot of ways to figure out the endpoint. I think that's what my next bullet is. Well, yeah. Once we're at the endpoint, right here in the lab, we're going to use an indicator so the solution turns a pink color when we get to the endpoint. You can use different indicators for different things, or you can just measure what the pH is at the endpoint if you want to do it that way. There's lots of ways in there. We're going to use phenolphthalein as our indicator, which is going to be pink. Okay. Once we know what the endpoint is, we can determine the volume of the solution added. Okay. We're going to do this by, if we're reading the burette, we're going to say your final spot minus your initial. Okay. And this is typically going to give you what is added. This should give us what is added in terms of milliliters. If we're working a problem, I'll probably give you how much volume was added. In the lab, you'd have to figure it out by reading the burette. We did that at the beginning of the semester where you can take the difference between the 2 points. Lastly, once we know how much is added, right, because we'll know how much is added, we'll know the concentration of base, and then we can use that to find the concentration of the original sample. We're always going back to figure out that original sample when we're talking about quantitative analysis, all right? One thing that's crucial in this experiment is knowing the concentration of the titrant. Okay, you must know this precisely. And so a good way to do this is called standardization. Okay. This molecule here is called KHP, potassium hydrogen phthalate. Um, we're not going to worry about spelling it. It's crazy, but it's a it's an ion of a diprotic acid. There's another ionizable hydrogen right here, and this functions as a monoprotic acid. This is typically used in standardization. So you'll use a known amount, known grams of KHP in solution. Okay, we're going to titrate this with whatever base we're using. In this example, we're using sodium hydroxide. Okay, titrate this with base. And then from there, we can figure out what the base concentration is. Okay, essentially, we have to do it most of the time. We're going to have to do a titration at the beginning to figure out the concentration of the titrant we're going to use in the titration to figure out our unknown. Okay, so the first one is a standardization to figure out what the OH minus concentration is. Okay, the OH minus concentration fluctuates because this will react with CO2 in the air and it will reduce the concentration of OH minus. Okay, so even though maybe you've made a solution and you've weighed out enough grams to have, say, a 0.125 molar solution of sodium hydroxide, once you've used it a little bit or once it's sat around a little bit, that concentration is going to go down over time. Okay, and doing the titration with KHP is a way to measure what the exact concentration is so that you can do your titration to figure out what the acid concentration is. All right, let's work an example and maybe my words will make sense. Okay. So here's a standardization reaction example. We're going to take 25.49 milliliters of sodium hydroxide, and this is what we need to completely react with this much KHP. Okay. Our question is, what is the concentration of sodium hydroxide solution? And if you remember way back when we started talking about these things, when your answer is concentration, you're going to have to do three things for me. You have to figure out moles of whatever we're looking for. So in this one, we need moles of sodium hydroxide. We're going to need liters of sodium hydroxide. And then we're going to say moles divided by liters equals whatever concentration we're dealing with. Okay. So let's take a stab at this. First up. Yeah. Okay. One, we're trying to figure out moles of sodium hydroxide. This is going to involve the reaction. Okay. This is the reaction we're doing. It's the neutralization of KHP. Right? This is KHP, reacts with hydroxide, gives us this thing and some water. Okay, this is stoichiometry. We can set this up using dimensional analysis. Our starting point is the grams of KHP because we're looking for sodium hydroxide. Our equation needs moles, and so we're going to convert this to moles of KHP using our molar mass. So this is 204.23 grams of KHP. Once we have moles, we can use our equation. 1 mole of KHP is 1 mole of OH minus. Okay. Right. I guess since I have it here in OH minus, we should do this conversion too. 1 mole of OH minus is in 1 mole of sodium hydroxide. Right? Because they're 1-to-1, they're the same thing. But since I asked for sodium hydroxide, we probably need to figure out sodium hydroxide. All right. let's do this. This looks more straightforward than it seems. But we need, even though all of these steps out here are one-to-one, we need to have them in the work so that all of our units and formulas will cancel out. Okay, because we're looking for moles of sodium hydroxide. Okay, 0.7137 divided by 204.23 times 1, blah, blah, blah. So this should give us 0.00349,459 moles of sodium hydroxide. Okay. Our mass has 4 significant figures, so we need 4 significant figures in our sodium hydroxide. Okay. All right. Let's now figure out liters of sodium hydroxide. Okay. This is the volume that was given. Okay. This is how much hydroxide we needed to do the reaction. So all of this moles is in 25.49 milliliters. Okay, so that's going to be the start for our problem. 25.49 milliliters. We don't need sodium hydroxide here. All we're doing is, well, the label here. We don't need the label here because all we're doing is converting to liters, and we've done this a billion times. 0.02549 liters. This has 4 significant figures already, so we're good. Our last step then is going to be find the concentration. And so we'll take the moles we just found, 0.0034945 moles, and divided by the volume we have, 0.02549 liters. All right, there's our moles divided by 0.02549. So this sodium hydroxide concentration is 0.1370964 molar sodium hydroxide. To 4 significant figures, then this is 0.1371 molar sodium hydroxide. Okay. This is, I label it as a standardization problem, but this is a titration problem. Okay. We're going to do another titration problem now. Okay, this is a titration problem. You'll have one of these on an exam coming up at some point, so let's make sure we know how to do these two. This is the same kind of idea as what we just did. Okay, let's look at this. We have 3556 milliliters of unknown H3PO4. So this is where the of is, so those go together. It's titrated with 0.125 molar KOH. The endpoint was determined to be this of the titrant. So we need to figure out what is the titrant in this case. Okay, well, the titrant is the thing we know the concentration of. So the titrant in this case is sodium hydroxide. So this goes with this, and the 3556 goes by itself. Okay, I'm going to caution you here. This is 2 volumes and a concentration, and it looks like a dilution problem. But do not use the dilution equation. You will get a 0. Okay, because this is a titration, not a dilution. You cannot use the titration. You cannot use the dilution equation on a titration problem. Okay, all right. But our question is, what is the concentration of H3P? Ooh, I drew with my finger and not my pen. Okay, the concentration of H3PO4. Okay, so again, H3PO4 is our answer. So we don't want to start with it. We're going to start with the titrant. Always start with the titrant because that's what we know. Okay. Again, we have to do the same steps. We need to find moles of H3PO4. We need liters of H3PO4, and then we're going to do moles divided by liters to get our concentration. Okay. All right. So first up, moles of H3PO4. This is we're going to require a reaction. I didn't give us a reaction, so we need to come up with the reaction. We can do this. We know how to predict a titration, a neutralization reaction problem. Okay, let's write it out. H3PO4 aqueous. Okay, it's reacting with KOH. That is also aqueous. Because we have hydroxide with an acid, we're going to get water. And the salt of the crap that's left over is potassium phosphate, K3PO4. That is aqueous. Okay. Now, make sure this dude is balanced before you get much farther into this. Okay. Let's take a stab at this. We need 3 hydrogens, so we'll need 3 here. That gives us 6 hydrogens, so we'll need 2 of those. We'll need 2 of those. That means we're going to need 6 KOHs. That feels weird to me. 6, 2, 6. Three waters. I've screwed something up. Why can't I balance equations? Okay, here we go. No, that's not 8. That's KOH. I erased too much. All right. Oh, yeah, we need 3 waters. That's my problem. 3 waters. Because we have 3 H's. That's 3 H's and 3 OH's. There's my idea here. I forgot the extra hydrogen there. Then I lost my K here. All right. Gives us 3 potassiums, so that's okay. Phosphate, that's okay. So we just need 3 KOHs and 3 waters. Okay. This reaction is not a one-to-one reaction. All right. Now that we have that, we're going to figure out how many moles of phosphoric acid we're going to have, and we're going to start with the titrant. So that means we're starting with KOH. Always start with the volume. Because you can't start with molarity because there's more than one unit in there. Remember, capital M is moles per liter, not moles. Okay. Then we got to convert to liters. Okay. Once we have liters, we can use our concentration. So that's 1 liter of KOH is 0.125. That's 2 moles of KOH. All right. And then once you have moles of KOH, we can say there are 3 moles of KOH needed for every 1 mole of phosphoric acid. Okay. So let's math this out. 26.46 divided by 1,000 times 0.125 divided by 3 is 0.0011025. This is moles around room of KOH. This should have 3 significant figures, so right there. Okay. Now that we have moles of KOH, we need to figure out liters of solution. Okay. This is the unknown samples volume. Okay. So we're starting, that's our 35.56. 35.56 milliliters. Again, we don't have to show the formula in our calculation because we're not changing what we're doing. You want to also make sure you're not using the same concentration for both steps because you're going to end up going in a circle and it's not going to work. Okay. Let's see, our last step is to take moles divided by liters to get the concentration. Our moles, we just figured out 0.0011025 moles. And our volume is 0. 0.0556 liters. 356. The calculator is 0.031003937 molar H3PO4. Four significant figures. 0.03100 molar H3PO4. There it is. Okay. If you have any questions, let me know. This is tricky. You'll have at least a titration problem on an exam, and we need to know how to be able to do it. Hopefully, getting our hands dirty with this in lab will also be helpful. Okay. I'll catch you later. Let me know if you have questions.